Publish etmeyi düşünüyorsunuz.
Ya bunu kullansam sana mesela uyumlu mu?
Yok, kullanın direkt. Yani
ya bana olarak kısa omega'nın var da bu under dersler ne için geçerli oluyor böyle?
şimdi hoca yani soruları kimin okuyacağı değil. Bana böyle bir şey söyleseniz yaparım da yani biz bu derste kabul ettiğimiz şey şu distance D 3/D veya 4/D.
Ama işte yani bekliyorum ben. Normalde
siz T'li terimin etkisini falan da yapıyorsunuz. Doğru, evet. Daha doğru bir şey olabilir ama yani bu derste böyle yorumluyoruz.
Sınavda peki yazsam olur mu böyle kenara ben hemen böyle matbaatta yazdım.
Olur. Yani
bir deneyim alacağım.
Okey. Hazır mısınız? Sınavdan önce çok güzel oluyordur eminim. Başka konularda ders dinlemek ama. Üzgünüm. Ben nefret ediyorum aslında. Yani bu sıkış tepiş derslerden. Yani keşke şöyle 2 dakikacık bir zamanım olsa da derste öğrencilerle bir interaksiyona falan girebilsem veya daha böyle geyik yapabilsem yani. Hiç öyle bir şeyim yok maalesef. Çünkü derslerim sıkış bir bölümde. Yani ben burada 5 dakikayı yapsam, 302 ile ilgili bir şey söylemesem kendimi suçlu hissediyorum. Çünkü diğer section uçmuş gitmiş olacak falan. Maalesef böyle bir durum var. Hoşuma gitmese de ekmek parası işte yapacak bir şey yok. Okay, so here we would like to find the imaginary axis intersections here. Okay, so in order to be able to find the imaginary axis intersections, there are 2 methods, as I told you. The first method is just to use this property. So we know that at an imaginary axis crossings, we are actually going to have 2 roots like plus minus j omega. Okay, that actually means that into this equation I can substitute s equals to j omega, and then I can try to solve this equation for omega and k. Okay, that is going to be one of the methods here. So here let us try to look at this system in this case. So I have 1 plus k 1 over s cubed plus 2s squared plus 3s squared plus 2s. Then I equate this thing to 0. So I have s cubed plus 3s squared plus 2s plus k is equal to 0 here. So we see that in this case I can substitute s equals to j omega into this equation, and I can then try to find k and omega. This is the first method that we can apply. So note that here this equation is nothing but d of s plus kn of s is equal to 0. This thing is my d of s for this example, and k times n of s is 1 for this example. Okay, I have written the characteristic polynomial of the system, and then I have substituted s equals to j omega, and then I equate the result to 0. So we see that my unknowns in this case are omega and k. I have 2 unknowns, but I still have a single equation. How am I going to solve for that? In this case, yes, this single equation, we don't have a single equation in this case actually. We have double equations disguised as a single equation. Okay? So because this equation, when I substitute this j omega here, it's going to have a real part and it's going to have an imaginary part. And then I'm going to equate both of those to 0, which are going to be 2 equations, 2 unknowns. Then I will be able to solve for omega and k. So now let us try to substitute j omega here. What is cube of j omega? Minus j omega cube plus 3 j omega squared. What is j omega squared? It is minus omega squared minus 3 omega squared plus 2 j omega plus k is equal to 0. Okay? And now I can collect the real and imaginary parts together. K minus 3 omega squared plus 2j, I can take j omega parentheses here. In j omega parentheses, I have 2 minus omega square is equal to 0 here. So now I see that this is my real part and this is the imaginary part. If I equate the real part to 0, then it's going to give me k is equal to 3 omega square. And if I equate the imaginary part to 0, it's going to give me omega is equal to 0 and omega square is equal to 2. Okay? So now I can use this equation to substitute omega is equal to 0, which gives me k is equal to 0. Okay? And then I can substitute omega square is equal to 2 in this case, and k is equal to 6. Okay? So in this case, we see again two solutions. Which of these two solutions will be relevant for the root locus? Which one of these solutions? Both of them are going to be relevant for this root locus. Because k is equal to 0 is this point. At k is equal to 0, I have an intersection with the imaginary axis at the origin. Okay? That is the solution omega equals to 0. Okay? So at k is equal to 0, we find this solution here. And at k is equal to 6, we find this solution. So I know that here k2 is actually 6, and this point here is j square root 2, and this point is minus j square root 2 here. Okay? So in this case, I can actually say that. So based on this information, I can actually give the stability range of this system. If k is between 0 and 6, I know that the closed loop system is actually going to be stable. So now this was the first method, and the second method is going to be related to the route stability criteria. So here let us write the second method. In the second method, I'm going to calculate the following. So I'm going to apply route stability criterion to this polynomial. Okay? So I'm going to apply route stability criterion to this polynomial. So let me write this like this. I have s cubed, s squared, and s, and I have 1 here. So if I find the first row, it is going to be 1 here, and I have here 2, and I have here 3, and I have here k. Okay? This is the route array that I will be interested in. So what about the pole topology that I'm looking for? In this case, at that specific k value, to find that specific k value, at that specific, at that specific k value, we have this pole topology. Okay? What type of difficulty do we expect in such a case? It is a second type of difficulty I'm expecting. What did we say when we saw second type of difficulty? Second type of difficulty is caused by radially symmetric closed loop poles. Okay? So the closed loop poles can be, for example, coming in this topology. They are in that case I have radially symmetric closed loop poles. Or they can come in this topology. Okay? Again, this is the thing that we are interested in. Or they might come in this type of topology. In any of these cases, we will be expecting a second type of difficulty from the route array. And we know that when we encounter a second type of difficulty, actually we can go one row above and we can define an auxiliary polynomial. And the roots of that auxiliary polynomial would be the roots causing the difficulty. Okay? So here, I am looking for a difficulty which is caused by this type of roots. Okay? What does this mean for the degree of the auxiliary polynomial? If these two poles are causing my difficulty, what should be the degree of my auxiliary polynomial? It should be a second degree polynomial, meaning that my auxiliary polynomial will be somewhere in this row. Okay? And then where should I encounter the difficulty? One row below. Okay? I need to encounter difficulty here so that I have my auxiliary polynomial defined by a second order polynomial. Okay? So that actually means that if I can make this last S row exactly equal to 0, all of the elements, then I'm going to be enforcing a second difficulty on this polynomial. So now let us try to calculate this row. It is 6 minus k divided by 3. So, and what we can do here is that I can equate, and this is the only non-zero element in this row. All of the other elements are already 0. That actually means that if I equate this row, this number to be equal to 0, then I'm going to be enforcing a difficulty of second type. Okay? And we see that if I enforce that difficulty, then k is going to be equal to 6. Then how can I find the intersection points on the imaginary axis? I can find k by using this idea, and it is 6. I have found it, which is the same as the one that I calculated before. How can I find the imaginary axis intersections? Then I can go up and I can define my auxiliary polynomial. Okay? So now I can go one row up, and then I can define my auxiliary polynomial. P of s is 3s squared plus k, and I have already calculated what k should be. It is 3s squared plus 6, meaning that I have in 3 parentheses 3s squared plus 2 is equal to 0, and the roots of this thing is plus minus j square root 2. Okay? This is just the second method for finding the imaginary axis crossings. Any questions here? Yes.
If we go one step further, like k at the first entry of the router, can we find another k value from that's causing a difficulty?
In that case, you can actually do that, but in that case, you would find only the pole at 0. Okay? So here, that coefficient is going to be k, and you see that it is going to be a single root that is causing the difficulty, and it's the root at s equals to 0. Okay, that is what you can do. But here, when we try to find the complex roots, we always try to make the auxiliary polynomial an even-ordered polynomial, and it's specifically a second-order polynomial we are looking for here. That is why we are equating this row to be equal to 0. If you want to encounter it somewhere else, then you are enforcing, then your auxiliary polynomial is going to be first-degree polynomial, meaning that you are going to get only a single root there. So this actually completed the rules of root locus that we are going to see. So now I will just give a general overview of the rules that we have found. So let us write general rules for root locus. So here I will consider the general case. So let us say d of s is an nth order polynomial, okay? And let us say n of s is an nth order polynomial. We know that in this case the characteristic polynomial is going to be d of s plus k n of s. This is our characteristic equation for such a system. So here, if you look at the rules of root locus, we have number of branches or number of trajectories. In this case, we are going to have, this number is going to be the maximum of m and n. Okay? So I have, if this is nth order and this is mth order, then the number of closed loop poles will be just the maximum of this number. And usually, in 90% of the cases, n is actually the larger number. Okay? That actually means that usually this number is n. And we have calculated the start points at k is equal to 0. These start points are at open loop poles. Okay? And the end points, this is when k goes to infinity, and these are open loop zeros. And the branches that do not start at an open loop pole or end at an open loop zero start or end at s going to infinity, at the asymptotes. Meaning s going to infinity. So if a trajectory does not start from an open loop pole, and if it does not end at an open loop zero, then that means that trajectory is either going to start at infinity or end at infinity. So suppose that I have the following figure. Suppose that I have two zeros, okay, and suppose that I have one open loop pole only. Okay? In this case, the number of open loop poles is less than the number of open loop zeros. Okay? In this case, I can fill in the real axis again. Okay? And then I can put my arrows going away from the open loop poles and going towards the open loop zeros. Okay? Now I know that there will be two trajectories in this case. There will be two branches. And one of the branches will end here. The other branch is going to end here. Alright? And one of the trajectories is going to start here. Where is the other one going to start? Where is the other one going to start? It's going to start at infinity. And there will be a single asymptote of this one. And the other one is going to start at infinity. And we're going to have a root locus looking like this. This is what this general fact is actually telling us. Okay? So if one of the branches is not starting at an open loop pole, or if it's not ending at an open loop zero, then that actually means that it's going to either start at open loop at infinity, or it's going to end at infinity. We have already seen examples where the root locus ends at infinity. This is one of the examples when root locus starts at infinity. Okay? Another fact here, the root locus is symmetric with respect to the real axis. Why is this the case?
All are always symmetric.
Sorry?
All are always symmetric.
Yeah, why?
Because there is no imaginary coefficient.
Yes. So here, this polynomial has always real coefficients. Okay? So all of the coefficients of the characteristic polynomial are real, meaning that if we have a complex pole, then its complex conjugate is also going to be a pole. And here, and that actually means that the root locus will always be symmetric if we have it with respect to the real axis. And if we have a pole at some point, then we're going to have a pole at its complex conjugate for the same k value. We have the root locus on the real axis. In this case, the number of open loop poles and zeros to the right must be odd. This was the rule that we have learned and applied so far. The number of asymptotes is n minus n absolute value. And the angle of the first asymptote is 180 divided by n minus n. Angle between asymptotes, it is 360, always twice this number. And the intersection points of the asymptotes is sigma 0, summation of the open loop poles minus summation of the open loop zeros divided by n minus n. We have found the rules for breakaway endpoints. We have actually we can calculate them by using the formula d over ds k is equal to 0, and then we can substitute the results into one of the formulas given like this, or k is equal to minus d prime of s divided by n prime of s. As long as one of the denominators is not equal to 0, you can use one of these formulas. And finally, we have intersection with the imaginary axis. And in this case, there are two methods. The first method is d of s plus k n of s. When we substitute j omega, the result should be equal to 0. This is the first method. The second method is Rao-Hurwitz stability criteria. Yes.
In the system you drew, you mentioned that some of the root locus might go inverse and then follow the asymptote.
Yeah.
So we should check it. If that doesn't happen at the imaginary axis, how can we check that?
So here, when you substitute j omega in that case, so the root locus was given something like this. Okay. So here I had two closed loop poles here, and there were the asymptotes looking like this. Okay, so 4 asymptotes, and I had this root locus. So here let us try to write this thing. So I have d of s. In this case is s squared and s plus 1 and s plus 1. Okay, and I have n of s. I can take it anything but any non-zero number, but it is 1. Okay? So I have this thing, and if I write now the characteristic polynomial, it is going to be d of s plus k n of s is equal to 0. Okay? And in this case, if I write d of s, I can write s to the 4 plus 3s cubed plus 2s squared, and I can write k is equal to 0. Okay? This is my characteristic polynomial now. Now let us try to substitute s equals to j omega. So I have omega to the 4 minus 3j omega cubed minus 2 omega squared plus k is equal to 0. Alright? So now let us try to look at the real and the imaginary parts. So I have omega to the 4 plus minus 2 omega squared plus k is equal to 0. This is the real part. And the imaginary part is minus 3 omega cubed is equal to 0. Okay? In this case, the only possibility is omega is equal to 0, and when I substitute this, then k is going to be equal to 0. What does this mean?
There is no crossing again.
There is no other crossing. Okay? You won't find that solution when you substitute j omega. That solution will not appear. So I know that this thing is going to be something. There is also another way for finding this. How can we do it? Again, apply route stability criterion. So here, s to the 4, s cubed, s squared, s, and 1 here. Okay? So I have s to the 4, 1, 2, k, and I have 3, 0 here. Okay? And now we can write 6. So I have 2 here, and I have k here. And I have 2 minus 3k over 2, and I have k here. Okay? When do yes? Ben yanlış bir şey mi cevaplıyorum şu anda?
Biraz.
Peki tamam.
Yani ben zaten diye sormuştum soruyu. Bu olay imaginary axis'te gerçekleşmiyorsa, yani mesela bizim pollarımız, polumuz sıfırda değil mesela, 1'de veya 2'de. Hani geriye doğru gelip gelmediğine, polinomu sıfıra doğru öteleyerek mi bakacağız?
Evet, yani esasında onun nerede olmasını, yani mesela şunu yapabilirsiniz aslında. Yani bu şöyle bir şekilde geliyor olsaydı, bunu birazcık, şu ekseni birazcık bile shift etseniz, artık iki yerde kesişim bulacak gibi bir şeyiniz var. O şekilde yapabilirsiniz. Veya aslında bu derste öğretilmeyen başka bir şey var. Yani eski notlarda falan var, görürsünüz. Departure angle veya departure angle diye bir konsept var aslında. Yani şu polun tam şu noktadan ne kadarlık açıyla çıktığını bulabiliyorsunuz. Angle condition diye bir şey bulmuştuk ya. Angle condition diye bir koşulumuz var. Root 9'un üzerindeki her noktada o angle condition sağlanmak zorunda. Şu root'tan epsilon kadar uzaklaştığınızda ne kadarlık açıyla uzaklaşmanız gerektiğini departure angle denilen bir şeyle bulmanız mümkün. Ama dersin şeyine dahil değil, içeriğine. So here, what can you say about this? When I equate this thing to 0, I see that the only intersection. So if I have this intersection like this, okay? If I had this, then for some k value, I would have complex conjugate poles here, and here, okay? And that actually means that I need to have a second type of difficulty. If I equate the S row to 0, then I see that k can only be equal to 0. I can encounter the second difficulty only when k is equal to 0, which is when both of these closed loop poles are here and here. Okay? dayanın birazcık dakika. 15 dakika daha dayanın. 2 dakika verelim. So we are going to do this root locus in non-standard form. I'm going to illustrate this on an example. In the notes there is another example as well, but this is going to be something slightly easier one. Suppose that I have a system, I have a control system given like this. Okay? So remember, and the task is to draw the root locus with respect to k when k changes between 0 and infinity. Okay? Such a case is called a root locus in non-standard form, or with non-standard form transfer function, let us say. Why is that? Why is it not in standard form?
K times.
Yes, we always had the following case. The open loop transfer function, so far, for the examples that we consider, it was always in this form, k times n of s over d of s. Okay? The system open loop transfer function was always in this form in the earlier cases, and this is called the root locus in standard form. Okay? And in that case, I have calculated the characteristic polynomial 1 plus k n of s over d of s is equal to 0, and the characteristic polynomial was given as d of s plus k n of s is equal to 0. This was the standard case. But in this case, I see that k parameter in the open loop transfer function, it is no longer in the form of a gain, and I have a ratio. So we see that k enters multiple times, and it is both in the numerator and the denominator. Okay? In this case, I cannot really try to draw the root locus as follows. So I can actually try to, where are the open loop poles? Open loop zeros are at 0. Okay, I can put here 2 zeros. And where are the open loop poles? They are dependent on k. Where should I place them? So I'm drawing the root locus when k changes between 0 and infinity, and when k changes between 0 and infinity, these open loop poles will change their locations. Okay? So that actually means that I cannot put here fixed pole locations anymore. Okay? So really this is not the approach to continue here. I can no longer work with open loop poles and open loop zeros here. I need to do something else. So here let us try to calculate the characteristic polynomial of this new system. So I can calculate the characteristic polynomial of that system as 1 plus, I can write that k plus 4 s squared divided by s cubed plus 3s plus k is equal to 0. Okay? And then I can write s cubed plus 3s plus ks squared plus 4s squared is equal to 0. Okay? Now compare this characteristic polynomial with this one in the standard form. Do you think you can bring that characteristic polynomial into this form? You can actually, okay? So when the parameter does not enter in the form of a gain like this, we always try to standardize the characteristic polynomial into this form, okay? So what I do here is the following. I have s cubed, and I'm considering all of the terms without any k, okay? S cubed plus 4s squared plus 3s, and I'm considering all of the remaining terms related to k, okay? So I have k, and I have s squared plus 1 is equal to 0, okay? Now we see that this characteristic polynomial is indeed in the form of the standard characteristic polynomial. And I can consider my new d, I can say that it is d bar of s, okay? And I can consider my n bar of s as this one, okay? Now I can actually try to draw the root locus for this system. Where are my open loop zeros in this case, or things that would serve as open loop zeros in this case? They are at the roots of n bar. Okay, I know that roots of n are open loop zeros in the standard root locus, and roots of d are open loop poles in the standard root locus. So here, if I would like to find the terms related to the open loop zeros, would be the roots of n bar of s, and they're going to be at plus minus j. Okay. And here I have d bar of s. Roots of d bar of s would serve as my open loop poles. Okay? And the roots of this thing, if I take s parentheses, it is s squared plus 4s plus 3. And I see that this is s plus 1 and s plus 3 here. I see that the roots are at here and at minus 1 and at minus 3. So now fill in the real axis. Arrows. How many asymptotes? Only one, and it's going to point in 180 degrees angle. I see that this pole is already going to the asymptote. Okay? And then these two are going to approach each other for some k values, and then they're going to go to this. Right. How do I know that they're going to go there like that? Why not something like this? How can I test this? It's the same problem that we encountered before. Substitute s equals to j omega here and try to find the solutions. You would only find this one here at k is equal to 0. Okay? Or you would find another solution for negative k. Right? It might not be shown in the root locus here. Any questions here? Yes.
If there were k square in the block diagram.
In that case, you won't be able to do it. No. It has to enter linearly into the characteristic polynomial. Any other questions? Başka bir şeyle ilgili sorusu olan var mı? Dersle ilgili sorusu olan var mı öncelikle? Sorusu olup son 10 dakikada anlatmamı istediğiniz bir şey var mı?
Hocam root locus'un tam olarak yani bir şey hangi seviyede oluyor? Bir şeyler yaparak oluyor.
Efendim?
Bizim root locus
Algebra denilen matematiksel alan üzerine aslında temel olarak. Algebra, mesela fundamental theorem of algebra nedir biliyor musunuz? Fundamental theorem of algebra. Duyan oldu mu?
You have to numerator denominator in them.
Constant olmayan n'inci dereceden bir polinomun n tane kökü vardır. Fundamental theorem of algebra bu oldukça basic bir şey. Neden constant olmayan polinom filan diyoruz? Mesela sıfır polinomunun kaç tane kökü var? Infinite yani sonsuz tane kökü. Dolayısıyla sıfırı bir kere çıkartmamız lazım. Yani işte sıfır olmayan n'inci dereceden polinomun n tane kökü vardır gibi bir şey diyor. Fundamental theorem of algebra. Yani algebrada derinleştikçe bulunan şeyler bunlar aslında. Proof'unu bir şekilde iletebilirim sizlere ama ben bile üşeniyorum açıkçası şey yapmaya. Yani düşünün derste anlattığım bir konu. Baya böyle ağır bir proof'u var.
Oxford çıkınca biz buna bizim polinomumuzun tam katı diyoruz.
Evet yani bana da magical geliyor. Sizden daha farklı değilim o konuda maalesef. Başka anlatmamı istediğiniz bir şey yok. Bu pek yararlı olamadım burada. Başka yararlı olabileceğim bir şey var mı? Buyurun. Aha.
Bir row'un zero olduğundan bahsediyorum. Sadece yani mesela 2, 4 tane symmetric root olduğundan olabilir yoksa 1, 3 odd numbers of roots.
şimdi polinomunuzun aynı anda şeyi varsa, yani mesela şu da size verecektir muhtemelen. 0 da var, şu noktada var, şu noktada var, şu noktada var. Polinomunuzun 0'da root'u yoksa bu her zaman auxiliary polinomu even dereceli yapıyor. Ama polinomunuzun 0'da kökü olduğu takdirde o zaman auxiliary polinom odd dereceli olması mümkün. Zaten odd dereceli olunca hemen auxiliary polinomun 0'da kökü olacağını görebiliyorsunuz. Çünkü hemen şeyleri yazdığınızda constant terim olmadığı için odd row'larda hemen 0'da kökü olacağını görebiliyorsunuz. Dolayısıyla ve de polinomunuza baktığınızda zaten yani şu polinoma baktığımda ben şu k 0 değilse bunun 0'da kökü yoktur. Tamam mı? Yani dolayısıyla aslında polinoma baktığınızda hemen şeyi görmeniz mümkün. 0'da kökü var mı yok mu? Hangi k'lar için 0'da kökü var? Onu hemen görebiliyorsunuz. Onu gördükten sonra da artık even mı odd mu şeyinden kurtulabilirsiniz hemen. 0'da kökü olan k'larda odd'ları check etmeniz lazım. Öyle bir şey yapabilirsiniz. Başka sorusu olan arkadaşlar? Buyurun.
Sıfırdan farklı statistik error olan bir sistem kesin stabil olduğunu söyleyebilir miyiz?
Steady state error kavramı stability ile tanım. Stability ön koşulu steady state error. Tamam mı? Dolayısıyla şeyden bahsetmemize imkan yok. Steady state error'dan bahsetmeme imkan yok stable olmayan bir sistem için. Dolayısıyla birisi steady state error'ı 5 istiyorsa o zaman kesinlikle aynı zamanda stability de istiyordur. Yani yoksa stability'yi sağlamadan steady state error'ı 5 sağlamışız çok bir manası. Belki teorik olarak bir manası olabilir de pratikte bir şey değil.
O zaman mesela bize KO vesaire vermiş olmasına rağmen önce stable diye kontrol etmemiz mi lazım? Çünkü 2017 sorusuydu galiba. KP'yi vermişti ama Unis'te error'u yoktu çünkü unstable oluyordu. KP'yi vermiş olmasına rağmen.
Evet yani esasında steady state error kriteri verildiğinde orada implicit bir şey de düşünmek lazım. Aynı zamanda stability kriteri de düşünmek lazım.
Bu dersin kapsamında sinusoidal steady state diye bir şey var mı?
Hayır ama sinusoidal bizim internal model principle dediğimiz şey sinusoidal steady state için de geçerli. Bir sistemin sinüs sinyaline zero steady state yani böyle robotik sistemler var ki şey yapmanız lazım yani sürekli aynı hareketi yapmanız lazım ve onu steady state errorsız yapmanız lazım. O şeyi eğer bir sinusoidal'a steady state error istemiyorsanız loop'unda gene o sinüsün şey olması gerekiyor. Laplace transform olması gerekiyor.
Biraz bounded aslında.
Efendim?
Biraz bounded.
Evet. Yani sistemin kendisi o sinyali yaratabiliyor olması lazım. Kendi loop'un içerisinde o sinyali yaratabiliyor olması lazım ki sistem steady state error sıfır verebilsin. Yani içinde o sinüsün Laplace transformu olabiliyor olması demek, sistem loop'un içinde o sinyali yaratabiliyor demek aslında. Ve de ancak o zaman steady state error sıfıra çekebiliyoruz. Buyurun.
Kitapta eğer yanlış hatırlamıyorsam bu lifetime birine 0-9 arası mesela.
Evet.
Böyle bir şey tanımlar mı?
Derste birazcık bahsettim. Overdamped sistemler için rise time nasıl tanımlanır diye şey yaptım. Yani o durumda tabii ki klasik rise time tanımlamaya çalışırsanız rise time'ı underdamped'da nasıl tanımladık? Final response değerini kestiği ilk yer olarak tanımladık. Tabii ki overdamped sistem için bunu yapmaya çalışırsan infinity'de kesiyor. O zaman o rise time tanımlamak istersen bir manası yok. Infinity rise time'la ne diye uğraşıp durayım. O yüzden 0.9 y infinity dendi. İşte 0.1 y infinity dendi. Bunların arasında kalan zaman diye geçiyor. Yani bunlar için explicit form, başka bir arkadaşınız da sordu. Bunlar için explicit formüller de var galiba kitapta. Ama bizim bu derste pek kullandığımız bir şey değil. Eğer overdamped bir sistem olursa daha çok bizim için yani bunun şeyle artık bu noktadan sonra şeyle çok büyük farkı yok. Ha settling time kullanmışsınız, ha rise time kullanmışsınız. İkisi de time constant'ın belli katsayılarla çarpılması, 1/time constant'ın belli katsayılarla çarpılmasından filan oluşacak. Yani overdamped veya first order sistemlerde biz rise time kullanmak yerine daha çok settling time ile uğraşmayı tercih ediyoruz. O da işte sadece bir tane katsayıyla aradaki fark olduğu için çok bizim için önemli değil.
Mekanik sistemde iki inertia arasında damper ve spring varsa ama paralel bağlıysa. Yani şöyle inertia var, paralel bağlı spring ve damper. Nasıl bir yöntem diye soracağım.
Nasıl bir şey olacak söyleyin.
Inertia. Tamam.
Mass diyorum artık.
Aynen.
Mass bir.
Kablolar çıkıyor. Daha sonra paralel şekilde bir damper ve spring bağlı.
Şöyle mi? Şurada damper var. Şurada spring var.
Aynen. Gibi. Yani tek kablo birleşiyor. Damper var ya, bu da liste.
Bu çok
trivial, evet.
Bu çok şey değil. Yani bu zor değil. Asıl bunlar birbirine ekle bağlandığı zaman problem. Yani şu daha problem bakın. Asıl problem olan bu. Yani şunu yazmaya çalışırsam bu x1, x2 diyorum. İşte m1 x1 dot, double dot eşittir. Eksi, her zamanki kuralımı kullanıyorum. B, x1 dot eksi x2 dot eksi k, x1 eksi x2 yaptım. M2, x2 double dot eşittir. Eksi B, x2 dot eksi x1 dot eksi k, x2 eksi x1. Bunları hemen yazdım. Şimdi şu daha problem. Burada araya bir hipotezsel bir mass koymazsanız işler şey olur. Çünkü burada şunlar standart zaten. Burada araya bir tane mass koy. M diye. Şurada. Şimdi şey yaz. M1 x1 double dot eşittir. Eksi B. Şuna x diyeyim. Şuna x1 diyeyim. Şuna x2 diyeyim. M1 x1 double dot eksi B dedim. Ondan sonra şeyi yazdım. x1 dot eksi x dot. M'i yazıyorum. M x double dot eşittir. Eksi B x dot eksi x1 dot eksi k x eksi x2. M'yi de sıfıra götüreceğim bu arada. Tamam. Dolayısıyla şurası sıfır. Şunların eşit olduğunu buldum bakın. Ondan sonra m2 x2 double dot eşittir. Eksi k x2 eksi x. Tamam mı? Yani buradan direkt şeyleri görebiliyorsunuz. Yani şurayı sıfırladım. Artık bunlar arasındaki ilişkiyi görür hale geldiniz. X dot'lar arasındaki ilişkiyi. Ondan sonra şurada da bazı terimler var. Hatta bu size direkt şunu söyleyecek. Şuradaki terimle şuradaki terim arasındaki bir ilişki var. Yani şuraya baktığınız zaman şurayla şura arasında bir ilişki bulmaya başlayacaksınız. O da işleri birazcık daha şey yapacak. Ben bu iki problemi böyle yaklaşıyorum. Efendim? Evet, yani şu bizim standart yani. Şunda bir şey yok ama burada başka bir şeyler yapmanız lazım ki. Çünkü bak burada şey gibisiniz. Bir current source gene iki tane şey aynı circuit elemanı. Akımları aynı gibi circuit elemanlarının. Burada voltajları aynı gibi. Yani bir noda bağlanmış elemanlar var. Burada da currentları aynı gibi. Yani birisindeki force diğerine direkt etkileyecek gibi bir şey var. Diğer tarafa geçecek gibi. Dolayısıyla o ikincisi bence daha non-trivial bir şey. Bitti herhalde dersimiz. Teşekkür ederim. Critically stable dediğimiz sistem imajiner eksen üzerinde polları olan sistem diyoruz. Yani stable veya unstable olarak karakterize etmek isterseniz, iki klasa ayırmak isterseniz unstable bir sistem. Yani ismi biraz yanıltıcı. Tamam, critical stable, unstable sistem.
En son yazdım işte, non-standard form. Notlarda ne yazıyor? Ben ona tam şey yapamadım.